So in this lesson, we're going to be talking about mass spectrometers. Now, mass spectrometer is just a device that uses electric and magnetic fields in order to determine then the mass of charged particles. So there's going to be three main components that we're going to be looking at. So first of all, in the accelerator region, we have an electric field that's going to be speeding our particles up. So that's going to be this region over here. So you see we have a set of parallel plates. A charged particle goes into the region in between and gets accelerated then towards this parallel plate over here. The next one we have is our velocity selector. Now, velocity selector has two fields, an electric and a magnetic field, and that's going to select particles that have only one very specific velocity. And the last one is going to be the detector region. That's in this region over here, and that's going to use a magnetic field then in order to just determine then the mass of that particular ion. And so the different ions then will basically curve as they enter that region. So we're speeding them up through the accelerator region. A small number of them will go through this small hole. Those ones will enter then the velocity selector. A very specific velocity will go straight through this velocity selector, which then will be lined up with this hole over here. And then those ones will curve along their path then in this detector region. So we'll look at each of those individually, look at how we come up with directions, and then calculations then for each of those particular regions. So the first region we'll look at is the accelerator region. And this accelerator region then is just composed of two parallel plates. And so we see the battery down here. We have the negative terminal attached to this plate here, and then the positive terminal, the longer one, attached to this plate here. And what we do then is we then just eject the particles into this middle region, and they'll be accelerated then towards the one plate. Now this particular one is set up for positive particles. Again, ultimately we want them to go through this, basically, or a small number of this, at least to go through this small hole here. And so we're trying to attract things in this case to the negative plate, so these would have to be positive particles. But we can then just fairly easily just flip the terminal of the battery here, and so we can flip the positive and negative terminals, depending on whether we want then positive or negative charges. So we eject the charged particles then into that accelerator region. Now, one thing to remember as well, that they all have different velocities when they're injected in there, and they have different trajectories. So some might be moving this way, some moving basically towards that negative plate already. They're kind of moving in all sorts of random ways there. Now this electric field, when we apply it, it's going to cause all of them to accelerate towards this plate. Again, we want it to be the one with the hole in the middle because we want some of those particles then to go through here. So all of those particles are going to gain kinetic energy. However, the final speed of each of those then is going to be different. And that's just because of those different initial speeds and different initial trajectories. So we actually don't know what the speed coming out of here is. We can look at how much kinetic energy has been gained by this one, and that'll be fairly uniform. But the final speeds will depend to a large extent on what the initial speeds were. Now also, most of the particles aren't actually getting out of here. So any of the particles that kind of strike this upper plate here, so kind of in this region over here, or this region over here, they're just going to stop there, kind of stay in that region. It's only a small number that are actually going to go through this gap and then head over to the velocity selector. Now we don't use this region as often then to do our calculations. Typically we'll get our speed from our velocity selector. However, if they are showing up in a question here, we're going to use conservation of energy. And for our problems, we will assume then an initial speed of 0 and then a path that covers then the total distance from one end of the plates to the other. And that'll just simplify our calculations a little bit. Practically speaking, that's not quite true. Again, they'll have typically some initial speed there, but since all the particles are different, that's going to be hard to tell. So for these ones here, when we do our energy, we'll have, of course, EP on the way in, and then that'll all go then to EK on the outside. Now remember, for electric potential, Q times V is your potential energy, and then as always, 1/2 mv squared for the kinetic energy. Now one other equation that will occasionally show up here, sometimes rather than given the voltage, you'll be given the electric field, and so then you can do a simple calculation there. So this voltage here, then is equal then to the plate separation D times the electric field. And do you remember, we have two E's unfortunately here. So this EP, this EK, those are both energies. But this capital E down here, this is electric field. And make sure you're keeping those ones straight then. So once the particles leave the accelerator region, they end up in this velocity selector region. And the velocity selector region then is composed of perpendicularly aligned electric and magnetic fields. And so we see in this diagram here, we have two parallel plates. So a negative plate on the top, a positive plate on the bottom. And so then we get those electric field lines, which are then in green. And then we have our magnetic field, which is coming out of the page. So if your page is lying flat, basically straight up for those ones. Now, the other thing that must be true for these ones here is that the force based on that magnetic field and the electric force then based on that electric field, those have to act in opposite directions. And that's just so that we can set it up so that those two are canceling out, and then we have a particle then that can move straight through there with no deflection. Now for these ones here, gravity is not going to be an issue. The particles that we're dealing with are going to be too small to worry about gravitational forces. Now the last thing then is the path of the particles. And so when the particles enter that velocity selector, they must be on a path that is perpendicular to both that electric and the magnetic field. So the velocity vector, the electric field, or electric force, and the magnetic force, those three things are all going to end up being perpendicular to each other. Now, if we go to our diagram over here, we already know, or our velocity then, let me just write that in. Our velocity then is going to be coming in from here. So our accelerator region is over here. And so we have then that velocity vector heading in perpendicular to both then those magnetic field lines and the electric field lines. Now from the accelerator region, we know then that it was a positive particle that was in here. And a positive particle will be attracted then to that negative plate. And so for the direction for your force electric, you have to look at what is the charge on the particle, and then what plate is it going to be attracted to. If it's negative, it'll be attracted to the positive plate. If it's positive, it's attracted then to that negative plate. And so that's how you'll come up with the direction then for that force electric. Now for your magnetic force, you'll use your hand rules. So this is a positive particle, so you use your right hand. The velocity vector is pointing basically towards the right side of your page. So you put your thumb towards the right side of your page. Your magnetic field is coming directly up out of the page. So put your fingers of your right hand directly up. And what you'll find then is that your palm is pointing towards the bottom of your page. And that's going to be then your magnetic force. And so then towards the bottom, which is opposite the electric force, as we said, but you should be able to show that that's true. Then that force electric and force magnetic are acting in opposite directions. Now, as things go through there, this force magnetic is dependent on the speed. And so for one particular speed, this force magnetic will exactly match this force electric. And those are the ones then that travel straight through the velocity selector. And only the ones that travel straight through the velocity selector, only those ones will get to that basically detector region over here. And so that allows us then to know what is the velocity as they come through. And so what we're looking for is a case where the net force is equal to 0, and that force electric is equal then to that force magnetic. And when the electric force and the force magnetic are equal, those are the ones that are going to move straight through that velocity selector, and only those get to the detector region. So remember for these ones as well, for force electric, we're dealing with Q times E, and that's your electric field here, not energy, and then QVB for these ones over here. Now we see for this region, the charge actually doesn't matter, and the velocity moving through the velocity selector will be based just on that electric field strength over the magnetic field strength. And that'll give us then a fairly easy way of coming up then with the velocity then for those particles. Now this is for the case where those ones are balanced, where my force electric, in this case going up, but again you could set it up so it's going in another direction there. And then this one here, my force magnetic, are going to be then equal to each other. So force electric equals force magnetic. And then those ones will go straight through. Now, if a particle is moving too fast, it's going to curve away and leave the experiment there, but it curves away in the direction of the magnetic force. And so your force magnetic, because it's based on QVB, your force magnetic is velocity dependent. Your force electric, though, is just the charge in the electric field. So your force electric is actually going to be the same for all of those. And so if I have a force electric over here, but I have a force magnetic that's greater than equal, that's going to mean that I'm going to get a much greater force magnetic. And so the path that it's going to follow is going to curve downwards because I'll have a net force in that downwards direction. If it's moving too slow, remember that force electric is going to be exactly the same. So my force electric isn't changing, but I'll get a much smaller force magnetic. And so if it's moving too slow, it's going to curve in the direction of that electric force. So in this case, that will be upwards. But again, that could switch around depending on the diagram. Now again, all the ones that curve away aren't moving on. They'll just kind of leave the experiment. It's only these ones for which the velocity gives you an equal force electric and force magnetic that you're going to see particles then heading straight through and then entering the detector region. Now once the particles leave the velocity selector, then those that are going the right velocity will enter this detector region. And your detector region then is just composed of a magnetic field that's going to be perpendicular to the motion of the particle. Now, when they go through there, we know from our last section that we have then a charged particle in a magnetic field will follow then one of those centripetal paths. And because they're all going the same velocity, and that's determined by the velocity vector, if I have multiple ions going through here, I'm going to get multiple paths just based on their mass. And so larger masses will carve out a larger radius of curvature, and smaller masses then a smaller one. And so what we'll do for these ones here, we'll just use that net force equation and our circular motion then. So we'll use that v squared over r then to come up with then the direction or the mass of the particles in this region over here. And so if we look at our force net, that'll just be equal then to force magnetic, and gravity and such things won't matter in this region. My force net will be mass times acceleration, but that's in that centripetal acceleration. And this one here, as always, will be qv and b. And so that acceleration here is going to be that mv squared over r. So I'll have mv squared over r equals then qv and b. Now you can solve for any one of those ones here. But typically what we'll do is we'll cancel out those velocities, and typically we're looking for the mass. And so if we solve this one then just for mass, then we can get q times b times the radius all over top of then just the velocity. Now you could also solve for any other pieces. You could solve for, say, the radius of curvature of the magnetic field there, depending on what you're asked for. But we'll always set it up as mv squared over r equals then net qvb, and then solve from there. Now, one other note with this one here is what you're actually going to be measuring. So you'll have basically a piece of photographic paper then along this plate, or a digital sensor for maybe the more modern ones there. And as this then curves around, it's going to head through here, and then when it strikes the plate, it's going to then just register as a dot of light or as a target there. So just one thing, if you're reading that, this is not a radius, this is a diameter here. So if you are given the distance between where they're entering and where they're hitting, don't forget this should be a radius of curvature. This is given as a diameter. So what you're looking for then is half that then in that case. Now most of the time the question will just give you the radius of curvature, but watch for a diagram where it's marked as the diameter of curvature. Now just also watch here as you're going on here. If I put in my velocity vectors, those ones are all going to be tangent to the path. So those are all velocity vectors here. And then if I look in comparison for my force vectors are going to be perpendicular to that. And we'll see in that case then that always pointing towards the center of that circular path. And again, that's typical then of your basically centripetal motion there, where you always have then the force constantly changing always to the center of that centripetal path.